morning. The title is changing with respect to the program. So my presentation is with the analysis of the effect of temperature on fracture properties of shear memory alloys, pseudoelastic shear memory alloys. Then let me move to the aim and motivation of the work. The aim is to analyze the effect of active stress-induced transformation and testing temperature on fracture properties of shear memory alloys, pseudoelastic alloys, and this is because, as you know, mechanical behavior of shear memory alloys is significantly affected with respect to common metals, and in addition, this is the reason why we are here. Many aspects related to fatigue and fracture of shear memory alloys are still unknown, and this is due to the fact that stress-induced phase transformation, it is significantly affect the crack formation and propagation mechanism. The figures show schematic depiction of what is happening in the shear memory alloy and pseudoelastic alloy. Due to the high localized stress near the crack tip, we have a fully transformed martensitic structure, the twined martensite. Then we have a transformation region around the crack tip, and then the austenitic untransformed region. So within this context, we try to better understand the effect of phase transition mechanism on fracture and fatigue of shear memory alloys. So we started with numerical simulations by using finite element software code and special constitutive models for shear memory alloys, but we have also developed some analytical models based on modified linear elastic and elastic plastic fracture mechanic concept. But we did also experimental measurements by, fracture tests by using cracked specimens, and also fatigue dog bone specimen to analyze fatigue, structural and fracture fatigue of shear memory alloys. Now let me start with what we have done in this work. We have used the material, a commercial pseudoelastic material. The specimen is a single-edge crack specimen obtained by electrode discharge machining. We did a notch with a radius of 100 microns. And testing conditions are, okay, the first step is fatigue crack initiation. And after the crack initiation, we did this isothermal monotonic fracture test at very low loading rates. It is to overcome possible problem arising from local temperature change at the very crack tip due to phase transition mechanisms. And we analyzed the effects of testing temperature within the pseudoelastic regime of the alloy. It means between AF and MD. It is because the material in this condition exceeded the same microstructure, the twined martensite. So what we would expect is to get fracture toughness parameter, which is temperature independent under this testing condition. So we did both, we analyzed this specimen, we did both nanoindentation and digital image coloration measurements. And regarding nanoindentation, this is a picture of the crack tip with a matrix of indentation points. We used a special designed and a special loading frame to carry out stress and nanoindentation under stress and temperature control condition. And we used special parameters, in particular, large indentation loads equal to 400 millinewton, and a spherical indenter with a radius of 20 microns. This is to create a large process zone and to avoid to overcome possible problems arising from local measurement due to the heterogeneous structure of the material. Regarding digital image correlation, we used commercial software, the DIG software. And we used an objective, proper objective to get to analyze the crack tip of the material. As you can see, this is the notch radius, and this is the fatigue crack we obtained from preliminary cracking. So let me start with the nanoindentation results. We did preliminary measurements to analyze the response of the two crystallographic structure of the material, the martensite and austenite. And to this end, we analyzed two commercial material, namely type S and type M. They have basically a pseudoelastic material and Martensity shell memory material. And as you can see, as expected, the two material, two microstructure exhibit very large differences with very high recovery behavior of the pseudoelastic material as expected, and large pseudoplasticity in type and Martensity materials. So based on this observation, we identified two parameters: the residual depth after unloading and let me say, dissipated energy, the energy between the two, the loading and unloading parts of the curves. And based on these parameters, we should be able to analyze the locally the phase of the material. So what we did, okay, we did the matrix of indentation point near the crack tip, and these are the results at two different temperatures, 20 and 60 degrees Celsius. The contour maps are the contour maps of the residual depth after unloading, and as you can see, as expected, there is a significant effect of the temperature is expected. When increasing the temperature, the transformation zone decreases due to the Clausius-Clapeyron relation, and also there is a good agreement with the predictions of our model, which is just a very quick information. The model is based on the modified Irwin's correction of the linear elastic fracture mechanics, and is able to predict both the stress distribution in the austenitic and Martensitic region, the transformation rally, the transformation contours, namely Martensitic radius and austenitic radius, and also two values of the stress intensity factor, one describing the stress distribution in the austenitic and transformer region, namely austenitic stress intensity factor, and one describing the stress distribution in the fully transformed Martensitic region, which is namely Martensitic stress intensity factor. So let me describe the results on the AC measurements. The two figures reports the strain contours, the von Mises strain contours at 20 and 60 degrees Celsius obtained from the AC measurements. And as you can see, the dashed line reports also the quantitatively the contour, the transformation contours, and again we can see that there is a marked effect of the temperature, and also good agreement with our model. But basically the AC measurements were used to get the effective stress intensity factor. So we, in particular, we did the fitting of the AC data by the Williams expansion series. And in particular, we considered in the equation the rigid body motion and rotation, and also the distress terms. The figure on the right, on the left, report the contour plots of vertical displacements obtained from the AC, and on the right, the figure reports the vertical displacement without rigid body motions and rotations, and also comparison with the Williams solutions, the red dashed curves, and they are very good agreement. So let me describe the results from fracture test. We did isothermal fracture test within the pseudoelastic regime of the alloy, as I explained before, to three different temperatures, 20, 40, and 60 degrees Celsius. The figure reports the results, for example, typical results at low temperature 20 degrees and high temperature 60 degrees. And as you can see, there is always, in a large stable crack propagation at low temperature due to the large large transformation zone, and while fast fracture always occurs at high temperature. But when we analyze the critical values, maximum load, and the critical values obtained from fracture tests, we found a difference, a large difference between the case. We observed that critical value of stress intensity factor increases significantly when increasing the testing temperature.
So it is strange because usually large plasticity, for example, in common metals cause an increase in the stress intensity, in the critical value of the stress intensity factor. So to better analyze this effect, we try to analyze, okay, these results are, we better analyze these results. We try to compare the DAC results, the effective stress intensity factor obtained from DAC with linear acid fracture mechanics. And as you can see here, the figures report a comparison between linear acid fracture mechanics, the red curve, and the DAC are the dots. There is a large difference, especially at low temperature and high loads. This is due to the fact that when increasing the load and increasing the temperature, the transformation zone increases. While if we compare the results from DAC with our predictions regarding the obscenity stress intensity factor, they are very good agreement. So finally, let me show the results on critical values of the stress intensity factor. The figure report the critical values as a function of the temperature 20, 40, and 60 degrees. As you can see, the red curve represents the results obtained from linear acid fracture mechanics, while the blue curve represents the results obtained from our model, and also the point here, there are the point obtained from DAC. So there is a very good agreement. It is very strange because we observed that an increase, as I told you, an increase of the critical value stress intensity factor when considering linear acid fracture mechanics, while if we analyze the effective SIF and our model, this increase is not observed. It means that the model can be actually used to define fracture control parameters. So finally, what I want to say, this is we do think that great attention should be devoted in applied linear acid fracture mechanics theories to fracture and fatigue of chain membrane alloys, as they do not take into account the effects of temperature. And as you know, most of the work on fracture, even on fatigue crack propagation, use linear acid fracture mechanics, for example. So,
Thank you very much.